Hello, welcome again to the lecture series on Control Systems Engineering. In this session, let us discuss different types of controllers. These are the types of controllers normally that we use. One is called on-off controller, proportional controller, integral controller, derivative controller, proportional integral controller, PI controller we call it, proportional derivative controller, PD controller, proportional integral derivative controller, we call it as PID controller. Want you can play this video and then the explanation, understand the explanation of different types of controllers there. So, you see, as I have been explaining, this is the plant, then this is the controller, and we have feedback. So here we get the feedback signal, and this feedback signal is subtracted from the reference signal. You will get the error signal which actuates the controller. From controller, either you get manipulating signal, either we represent like this, or you may represent like this, U of S. This controlled signal operates the actuator of the plant. So the required variable is controlled here. So far we were representing plant as, let us say, G of S or GP of S. You call it as plant transfer function. This feedback H of S, let us represent this as GC of S, controller transfer function. Okay. So let us see how exactly the control action is created by the controller. Means what is the kind of signal it gives, how exactly the signal actuates the actuator and controls the plant variable. We have on-off controller, as I mentioned earlier, and these are the 7 different types of controllers. See, just to give an idea about what controller is, I have explained earlier the speed control of an engine. And here you have a linkage, a bar like this, hinged at this point. Correct? So I'm sorry, it is hinged here. Correct? It moves up or down accordingly. This will go like up like this or down like this, depending on the requirement. Accordingly, this will move up and down. This linkage, I call it as proportional controller. And here you have a cylinder arrangement, piston and cylinder arrangement with spool valve. This I call it as integral controller. And you have a spring and a damper. This I call it as a derivative controller. So in this system you have a proportional, integral and derivative controller. Okay, this controller in turn operates the valve. Accordingly, the engine speed increases or decreases. So let us understand clearly what we mean by proportional controller, integral controller and derivative controller. As I mentioned, I represent controller by GC of S, controller transfer function, plant transfer function, and the feedback transfer function. So here you have the error signal, controlling signal, that is your U of S, or manipulating signal. If the controller transfer function is simply Kp, it is proportional controller. For an integral controller, the transfer function is Ki by S. For a derivative controller, it is Kds. Proportional plus integral controller transfer function. Proportional derivative controller. Proportional, integral, and derivative controller. Okay. You can simply say it will introduce a pole at origin. It will introduce a zero at origin. In this case, there will be a finite pole. There will be a finite zero. This will be a quadratic equation, right? There will be two zeros like this. If I take LCM, it will become Kps plus Ki plus Kds square divided by S. So in the numerator, we'll get a quadratic equation. So let us see their actions now. On-off controller, it will switch on, off, on, off, on, off. That kind of controller it is. Simply we call it as on-off controller, a relay. On, off, like that. Here, I've just shown a proportional controller, this one. You see here, as the water level rises, the float will rise, moving this up. So about this hinge point, it will move like this, opening the valve, right? Suppose if I just consider a lever like this, and hinge point like this, let us say this is some xi and this is say x naught. Let us say this is b, this is a, this is x naught. So x naught b for equilibrium must be equal to axi. So x naught by xi is equal to a by b. This you can call it as gain Kp. So this how, like by adjusting the values of a and b, we can always have the value of Kp. Correct. Now this will be the transfer function of this. This is how it is, Kp. So you can think of even a potentiometer. Okay, potentiometer. Where output voltage will be proportional to input voltage like this. Now in this case, let us say G of S is equal to phi divided by S plus 1 is the planned transfer function. Just say this. Then G of S, and assume it is unity feedback, and GC of S will become 5 K S plus 1. Okay, suppose H of S is 1. Suppose steady state error in this case, limit s tending to 0, s tending to 0, s r of s divided by 1 plus g of s and gc of s. So suppose r of s is step input, that is 1 by s. S will cancel, then it will become 1 by g of s into gc of s. Let us say that is 5. K is nothing but say kp s plus 1. So it is limit s tending to 0. This is 0. Then this will be 5 into kp. Here will be 1 by 1 plus 5 into kp. Suppose if I increase the value of kp, denominator will increase. Error decreases. Steady state error decreases. But however, there will be a constant value, some value left, like it will not become completely 0. By chance, instead of this system is 5 divided by s into s plus 1. Say type 1 system if I take, then there will be s into s plus 1. This s is 0 means whole thing is 0. Something divided by 0 is infinity. Then the error becomes 0. As the type increases, error becomes 0. So this is the set value. This is the output value. Always there will be error. Okay. That error can be reduced if I can reduce the kp value. Okay. So this is what I have explained here. I think the same example. Only thing is I have substituted there in the previous slide g of s, h of s value, and I have shown that there will be error. So this is the response of a first order system, and you will get this error. This error you can call it as offset. So as I mentioned, as you increase the type number, error becomes 0. Okay. Let us look at what is an integral controller. Suppose you have a cylinder. Let us say there is a piston there. Okay. So into this some fluid is entering. Let us say Qi. This displacement is, let us say, x naught. This area, let us say A. So when some fluid enters, let us say it displaces by some distance. Okay. So x naught will be, we say, integral of the pressure that is acting on that P A, say the displacement is dx. So when we take Laplace, this will become 1 by s. Correct, no? So that's how this piston cylinder will act as an integral controller. Okay, the transfer function of this will be Ki by s. Okay, This is an integral action. So you can see here, as it goes up, or as the liquid level goes down, this will move down. Then this will move down so that the liquid can enter like this and operate the valve. Open the valve. Then more liquid can enter. Okay, now let us see what really happens. Say GC of S and G of S, that is equal to, let us say, Ki of S, and I'll take a system which is 5, let us say S plus 1. Okay, now assuming unity feedback, overall transfer function, if I take C of S by R of S, that will become 5Ki divided by S square plus S plus 5Ki. So it is a second order system now. So it will become oscillatory. That is the main thing. It is oscillatory. Response will be oscillating about the point. That means this fellow will move up. This water level will go up, go down like this. This becomes oscillatory. But error will not be there, but it becomes oscillatory. So that is the integral controller. So proportional controller will introduce offset, and integral controller, it will introduce oscillations. But error will be 0. Error will not be there, right? About the error point, it will be doing it. Derivative controller. Suppose if I take a spring and a dashpot, correct? And let us say this is xi, this is x naught. Because of this dashpot, the velocity will be x naught dot or xi dot minus x naught dot, or x naught dot minus xi dot. So if I take Laplace, it will become Cs, because first order derivative is there. Okay, so that's why here it is S. So a dashpot will act as a derivative controller. So now we can get this transfer function right. So now what happens is G of S and GC of S, you can say KD S. That is, the system I am considering is 5 divided by S plus 1. So KD S 5 divided by S plus 1. The transfer function will be 5 KD S. So S plus 1 plus G of S H of S, no? So that means 5 KDS divided by S plus 1 as 5 kds you get. So here what happens is that 5 kds, yes, no, 1 plus 5 kd, yes, plus 1. So this increases to zeta omega, means damping value. Correct? It will increase the damping value. So moment you introduce a derivative controller, it will introduce the damping. See here, when this goes up like this, goes and hits the valve, you can see here the displacement x increasing, then all of a sudden x value becomes 0. It will not control. Okay, it won't bother about the error at all. So only thing is it damps down the whole thing, right? So even if there is error, it will just get struck and it will not allow, it will not try to correct that error at all. Correct? So error in the sense this is a desired level. At any point, what is the liquid level? The difference is the error. It has to correct that error by opening the valve. But see here, x displacement will become simply 0. It will not correct the error. Now you know what is proportional controller is going to do. There will be always error. That error is offset. Then if you integral controller, if we consider, it makes the system oscillatory. About the main point, it will oscillate. KDS, it damps down. It will not correct the error. So now let us introduce that now KP proportional controller and integral controller with the plant. So this becomes your controller transfer function. Okay, all right. So this is Kp plus Ki by S multiplied by plant transfer function. You can have it. So here if you introduce the plant transfer function, you can understand what will be the error. Suppose it is step input, means R of S is equal to 1 by S I introduce, SS will cancel. It will become 1 plus Kp plus Ki by S. Correct? Introduce whatever transfer function you want. It is K by S. So that means in the numerator there will be S. S is tending to 0, something divided by 0 is infinity, 1 by infinity will become 0. Okay. Now, however, because of this, now the system order changes, it becomes oscillatory. Correct? Systems become oscillatory like this. There will not be steady state error. Okay, if you have only P controller, there will be steady state error like this. If I introduce integral controller, now you can see that steady state error is removed. However, the system has become oscillatory. It becomes very clear from the transfer function you get. So if you already have a proportional controller, it is giving error, then introduce integral controller, it will eliminate the error. However, it makes the system oscillatory. Now, proportional and derivative controller, if we introduce, what happens? Okay. So same way you start writing the transfer function here. Sorry. You can very clearly see that the damping value increases. So also the natural frequency value increases. So suppose you have an oscillatory system with certain error. If I introduce KDS, it will damp down. Okay, there is more damping. Slow response, you can see here. Is the peak time. Now this is the peak time. Response will be very slow. If I have all three, Kp, Ki by S and KdS, it is obvious this will introduce offset. This will eliminate offset but makes the system oscillatory, and introduction of this will make the system like oscillations will be damped down. So you will get smaller error, smaller overshoot, smaller steady state error. Okay, so this is the main thing. So the whole idea is then what is the difficulty here, and we understood only qualitatively, like what is the effect of each of this controller. But now question comes, what is should be the value of Kp, Ki, Kd, so that the system meets required steady state error, required or stated overshoot. Correct, that is very important. We state the steady state error should be so much, and overshoot should be so much, and you should settle down in so much time. Correct. If that is the case, what should be the values of Kp, Ki, Kd is what PID controller design is all about. Okay. From this, you can understand how exactly what are the effects of proportional, integral, and derivative controller and their combinations. Okay. So in the next session, let us study the effect of these controllers. I hope I give a clear idea about this. So here you introduce the planned transfer function, you find the steady state error, you find the response, you will come to know, which I have already taught how to do this. But as you keep on introducing all these terms, the equation becomes more complex. Probably solving such equations to find the response will be difficult. In that case, you better use MATLAB and see the response of the system. Okay? Right. Thank you very much.